Okay. Hello, everyone. I'm Lily, a PhD student from Beihang University. It is a great honor to attend this session. Today, I will talk about improving intermittent demand forecasting and empirical study of forecast combination methods. Here are the authors. First is me, of course, and the second is Yan Fei, my supervisor from Beihang University. And the third is Feng from Central University of Finance and Economics. Intermittent demand is a very common problem that is often observed in practice in the field of manufacturing, aerospace, chemical, and so on. Our half inventory consists of spare parts where intermittent demand is pertinent. What makes the demand difficult for forecasting is that there are two sources of uncertainty. The first is the obvious one, which will be our demand size that is unknown. And the second one is the uncertainty in the arrival of the demand when demands occur. So dealing with this uncertainty is quite challenging for forecasting and inventory management. The seminal work of the area of intermittent demand forecasting is proposed by Croston in 1972. He proposed a great idea that forecasts the size of demand and the inter-demand intervals separately. Then some scholars developed his thinking and put forward some modifications, such as SBA and TSB. Recently, Nick Locklear et al. First introduced temporal aggregation to intermittent demand forecasting and proposed ADIDA methodology. Then Petropoulos and his co-author further considered multiple temporal aggregation levels simultaneously, which is called AMAPA. Results in their work suggest that appropriate combinations lead to improved forecasting performance over a single method. However, very limited attention has been given to forecast combination methods for intermittent demand, which have achieved good performance in forecasting fast-moving time series in recent years. Then let's have a look back at forecast combination. Over the past half century, a lot of work has been done on forecast combination and achieved good performance. The seminal work by Bates and Granger found that forecast combination can improve forecast accuracy. Thereafter, numerous studies have worked around forecast combination with a variety of weighting methods, such as error-based approach, regression-based approach, Bayesian averaging, information criteria-based approach, and feature-based approach. More recently, Monteiro and his co-authors developed FOMA, which used 42 features to estimate the optimal combination weight based on the meta-learning algorithm XGBoost. Kong and her co-authors follow their work, but use diversities of forecast method to replace features because of its simplicity and computational efficiency. In our work, we aim to examine the empirical outcomes of a series of forecast combination methods and propose a diversity-based intermittent demand forecast combination framework to further improve the forecasting performance. To the best of our knowledge, it is the first time to analyze forecast combination methods systematically and research on combination models by learning in the field of intermittent demand forecasting. Then I will introduce our methodology for intermittent demand. The intermittent data are independent and have complicated uncertainty, which makes it difficult to capture its features. So diversity is a good tool for intermittent demand. We use a scaled diversity in Kong et al.'s work in 2020. The pairwise diversity between the I's and J's forecasting method is defined based on their total mean squared error and scaled by the mean absolute values of the historical observations. We follow their framework based on XGBoost and recite the forecasting pool and the optimal objective function for intermittent demand. Then we further proposed a diversity-based intermittent demand forecast combination framework as shown in this picture. Next, we perform an exhaustive comparison of the proposed approach and some representative combination methods through simulation studies. Because forecasting performance for all methods is highly affected by the increase of intermittence of the data, as well as the coefficient of variation. So we generate simulated series based on the three factors, IDI, CV2, and the number of observations, which are varied around 4 levels, as shown in the table. And 1,000 series are generated at each level. We examine in total 64,000 simulated time series in the following experiment, which can be implemented by the R package TS intermittent. In our work, we follow the SBC classification scheme, which is based on the above mentioned 2 factors, intermittence and variability. We plot the distribution of simulated time series. We can observe that the simulated data includes all the 4 classifications, and class 1 is the time series with low intermittence and high variability, and class 4 is that with high intermittence and low variability. Then we designed the simulated experiment as follows. First, we construct a forecast method pool for intermittent demand, including both in traditional forecasting method and intermittent demand forecasting method. Then we choose some representative forecast combination method to talk about for intermittent demand. They are simple average, median, optimal, lasso plus log, base 1 and base 2. The optimal method provides the weight in the sense that the variance of the combined forecast error is minimized. And we choose lasso for the regression method, which has been proven to be effective for forecast combination in recent years, and considered a logarithmic transform for forecast and the true values. And then the base 1 and base 2 are proposed by Bates and Granger, where the weights are only related to their historical performance. And base 2 assign greater weights to more recent errors than ones filtered in the past. In addition, we use 2 popular evaluation metrics, MASE and SMAE, and we produce forecast for the trial horizon. Then we present the forecast accuracy of above mentioned method in this table. We can find that AMAPA is the winner in most cases as the individual model, and this base forecast combination method do not perform well, except lasso plus log for class 1 with high variability. And the proposed method based on diversity always outperforms FOMA based on time series features. And the improvement is more significant for class 2 and class 4 with high intermittence. And the last line of the table presents the difference of learning based on 4 classes respectively and based on the all data during training the diversity-based model. The results show that classification is helpful to improve the overall forecast accuracy. Then we'll apply our approach to real data. It's about aerospace spare parts. The dataset has been previously investigated in the literature. It contains 5,000 monthly time series with 84 observations each. This picture describes the characteristic of the dataset. In the plot, the x-axis describes the percentage of zeros, and the y-axis shows the coefficient of variation of non-zero demand. We can observe that the time series exhibit high intermittence and variability. In previous studies, diverse forecasting error measurements are used for intermittent demand. The chosen measure of forecast errors influence what method that is observed to be the best. We sum up some related research in the table. So we may ask how to evaluate forecasting error measurements for intermittent demand. We classify the error measurements into two categories and choose some typical ones in our research. For traditional measurements of forecast errors, we choose these 4 scaled errors as shown in the first table. And for shortage measurement, we use scaled mean error, scaled mean period in stock, and the number of shortages as shown in the second table. Then let's look at the PCA loading plot for all error measurements. The figure shows that different measures represent different dimensions, which makes it impossible to reduce them to only one dimension without sacrificing information. As early as 2010, Wellstone and Zetterstedt emphasized that a single measure of forecast errors does not present the total different dimensions of the errors, so complementary error measures must be used. For point forecasting, we first use traditional forecast errors in the optimal objective function. We compare our method with the best individual model, simple average, median, and FOMA, and the results are presented in the table. We have some interesting findings. Our method is more significantly better than FOMA, especially for highly intermittent data. But our method cannot beat the best individual model based on SMSE because the weighted average loss function is not suitable for quadratic errors. We know that the SMSE is very sensitive to outliers, and it is not suitable for evaluating intermittent demand with high variability. So other absolute errors are more worthy of attention. However, due to the large number of zeros in the dataset, the optimization goal of minimizing absolute errors will cause that the predicted value tends to be close to 0, which will lead to an inventory shortage. So we introduce these 3 measures that can evaluate shortage. To solve the problem, we add a penalty item for NOS and propose a modified optimal objective. The following table shows the change of different error measures with different penalty factors. We can find that with the increase of alpha, the shortages decrease gradually, but the traditional forecast errors increase. As I talked about, there is no single method that will perform best on all measures because they provide complementary information. Fortunately, based on our approach, we can achieve a balance of reducing shortage and improving forecast accuracy by adjusting the parameter alpha, which makes our method flexible and practical in actual inventory management. Further, we investigate the uncertainty of intermittent demand forecasting. Here, we use the mean interval score, MNS, to measure the performance of interval forecast. The table shows the average MNS of different methods for 4 prediction intervals. The 50 and 67 prediction intervals provide a good sense of the middle of the distribution, while the 95 and 99 prediction intervals provide information about its tails, which are important for the risk of extremely high outcomes. We can find that our method outperforms others, which indicates that the diversity of point forecast is still very helpful for improving interval forecasting for intermittent demand. Finally, I conclude our work. Forecasting intermittent demand is very challenging because of its complicated uncertainties, and improving a single method is difficult. So we need to talk about forecast combination methods for intermittent demand. Then we have some main findings, and lasso plus log for the data with high variability, diversity-based approach for high intermittence, and classification for diverse dataset really work well for intermittent demand forecasting. And our approach can improve both shortage and forecast accuracy for actual inventory management. I have done with my presentation. Thank you to you all, and welcome to visit our lab. Thank you.
Okay, thank you, Lily, for this nice presentation. We have 3 minutes for 1 to 2 questions.
Thanks, Lily, for the presentation. Nice presentation. I have one question. So have you thought about evaluating your method on the M5 dataset, basically on the bottom level time series? Have you thought about that?
Thank you for your question. And do you mention other data set?
The M5, so the M5 dataset on the bottom level seems to be having intermediate time series. Have you thought about evaluating your method on that dataset?
We try 2 kinds of data set. The first is simulated data, and the second is a real data set about aerospace spare parts.
Okay.
Yeah, I don't think we have covered M5. It's good to do it in the future.
Okay, no worries. Thank you.
Yeah.
Yeah, I haven't tried M5.
Okay.
And thank you for your question.
Yeah, sure.
One more question.
Hi, Lily. Thank you very much for the nice presentation. My question is, when you compared your results with the former, did you use the same set of features used by the used in the original paper? Or did you modify the former framework, including the other features related to intermittent time series? Because in the former algorithm, we didn't include any features related to intermittent time series. So if you compare your results with the former, incorporating the features related to intermittent time series, that would also be great. Anyway, nice work.
Thank you for your question. We use time. We use diversity of forecast method to replace time series features in our framework, because the intermittent data is independent and it is very difficult to capture its features. So traditional time series features is not suitable for this kind of data. That is why our method outperforms format.
Okay, thank you. I don't think we have time for another question. And Lily is our PhD student. If you like her talk, you can please vote for our PhD student. Thank you. And now we move to third speaker actually. Lily, can you share your screen? Yeah, next speaker is Xiaoqian. She will talk about uncertain estimation for feature-based forecast combination. Xiaoqian, please share your screen.
Okay.
Yeah, please.
Thanks, Feng, and thanks the audience very much for your attending. I'm Xiaoqian, a third-year PhD student from Beihang University in China. Today, I will talk about the uncertainty estimation of feature-based forecast combinations. It's a joint work with my supervisor, Yan Fei, and the Fortius from University of Bath, and Feng from Central University of Finance and Economics. Next, I will introduce this work from the following 5 parts. First, I talk about the motivations of this work. As we know, time series forecasting includes point forecasting, which forecasts the mean or the median of the distributions for the future observations, and the probabilistic forecasting, which involve the associated probability related to the forecasts. And it's appealing because it enables the optimal decision making with a comprehensive understanding of both uncertainty and risk. Probabilistic forecasts involve 3 main forms, that is prediction intervals, quantiles, and density forecasts. And here is a simple example of the 80 and 95% interval forecasts. Regarding forecasting models, we have diverse sources, such as statistical models, machine learning models, and even judgmental models. When exogenous variables are not available, we can only use the historical data to train these models. However, we can extract features from the target time series to describe its characteristics, providing the decision makers more valuable information. For example, these features can include interpretable statistical features such as trend linearity, non-linearity, and also seasonality, and also other features extracted from, for example, time series images. So it's important to make use of these features information in the process of time series forecasting, leading to the feature-based forecasting. Since the seminal work by Bates and Granger in 1969, forecast combinations are increasingly used for the purpose of improving forecasting performance. And the supporting theorems include no free lunch and horses for courses, etc. These theorems actually state the fact that no model is perfect, and data don't come from one single model, and we need to select multiple models for target series according to its characteristics. And a work by Fortius and his co-authors in 2018, they summarize 3 sources of uncertainty, that is data uncertainty, model uncertainty, and also parameters uncertainty. And their empirical results show that only tackling model uncertainty is sufficient to achieve the significant performance improvements. So this supports the superiority of forecast combinations over a single model. Based on the aforementioned positive value of probabilistic forecasting, time series features, and also forecast combinations, it's natural to arouse our work. feature-based probabilistic forecast combinations. We identify 3 challenges need to be addressed. How do features affect the uncertainty estimation of forecasts, and how to guarantee the effectiveness of the relationship between features and the interval forecasting performance in forecasting a newly given data set, and how to translate this relationship into an attempt to improve the forecasting performance. Next, I go on with the feature-based interval forecasting framework we propose. This framework consists of a training phase and a testing phase. To forecast a test data set, a diverse set of reference data set is required first to train the relationship between time series features and the interval forecasting performance. Specifically, we separate each time series in the reference data set into a training period and a testing period. And the training period is used to extract features and train individual models to calculate the corresponding prediction intervals. Then the interval forecasting performance can be easily evaluated using a certain scoring rule given the testing period. And then we establish a model to link time series features with interval forecasting performance for each individual models. In this way, in the testing phase, we only have to extract the features from test data set and put them into the established link model. And the predicted scores obtained from the link model are transformed into a convex set of combination weights to produce the final forecasts. Moreover, we also design an algorithm for optimal threshold ratio search. It's designed to select an appropriate subset of individual models before forecast combinations. For the reference dataset generation, we follow the gratis paper by Yanfei and her co-authors in 2020 to generate sufficient and diverse time series to guarantee that the generated reference dataset has features as diverse as the test dataset, because our method is proposed and focused on feature space. And we consider the yearly, quarterly, and monthly subsets of M4 computation data as our test data set. And these 2 example plots show some time series in the reference and test data sets. And it can be observed that the length of historical data and the forecast horizons are different across different time series. For other components in our framework, we consider 42 features in TS features R package and 8 individual models such as ARIMA ITS, Tibet, and also others. And we apply MESIS to evaluate the interval forecasting performance because it considers the weights of prediction intervals and give a panel for the cases where the interval forecasts haven't covered the true values. And a smaller value of MESIS indicates a better interval forecast. About the model to link time series features with interval forecasting performance, we apply generalized additive model for each individual method because of its key merits such as interpretability, regularization, and flexibility in capturing both linear and nonlinear relationship between features and forecasting performance. And here here the logarithm form of MESIS is applied to extend its range to the real number set. Based on the established JM models, we can continue with some partial effect analysis. And I take out 3 examples to show our results. And the partial effect of one feature on the interval forecasting performance is distinct from the other features. And a feature has its unique way of affecting the interval forecasting performance of different models. Although sometimes all the individual models behave similarly with features changing. For example, the performance of ARIMA ITS and TBETS achieved significant performance improvements as the features seasonal strength and nonlinearity increase. And other methods behave oppositely. And all the individual models behave similarly with the autocorrelation efficiency changing. So some features are biased towards upweighting some forecasting models over others. Then we can dig out some valuable information from the established JM models and the partial effect analysis to determine the combination weights. Specifically, we apply an adjusted softmax function to determine the combination weights for reference dataset and test dataset. In this softmax function, exponential form is preferred because negative values can be downweighted to near 0. And as aforementioned, we design an algorithm for optimal threshold ratio search. So in this algorithm, we first define a threshold ratio TR, and for the I's time series and J's individual model, we calculate the ratio of weight and select individual models that satisfy the ratio of weight is greater than the threshold ratio. Then we can obtain the combined prediction intervals by taking a weighted average of individual intervals, and also obtain the combined point forecast by assuming the prediction intervals are symmetrical about the point forecast. Here is the result of optimal threshold ratio search. A larger threshold value indicates a smaller number of individual models are selected for forecast combinations. And in particular, the value of 0 indicates all the methods from the pool are selected. And the value of 1 indicates that only the method with the minimal fitted log misses value is selected. And from these 3 subplots, we observe that the average the misses value show an initial decrease and then increase as the threshold ratio increases. So this indicates that controlling the number of individual models used for forecast combinations is beneficial to improve the forecasting performance. And then I show the application results in M4 competition data. The rates of each model being selected show that ARIMA ITS and TBETS are frequently selected across different data frequency and also different confidence levels. And naive and S-naive are rarely selected. We also present the performance in terms of log misses for different confidence levels, and FUMA mean and FUMA weighted indicates our method with an optimal threshold search to control the number of individual models to be combined, and the FUMA or weighted indicates that all the individual models are combined using the weights we we have generated. So from this plot, we can see our proposed methods outperform all the benchmark models, such as individual models and also the simple averaging results. The forecasting results in terms of misses and miss value show that our proposed method consistently outperform the benchmark models for both point forecasting and also interval forecasting. So I conclude this work. Features are taken into account to estimate the uncertainty of forecasts, and we propose an optimal threshold ratio searching algorithm to select an appropriate subset of models for each time series and for forecast combination. And our approach outperforms a variety of individual models with distinctions for both point forecasting and prediction interval forecasting. And the related paper and our package and also these slides are available in these links. And thanks for your attention.
Okay, thank you, Xiaoqian. Any questions?
Andrei Vasnev here. Can you hear me? Can I ask a question?
Sure.
Thank you very much for an interesting presentation. This kind of topic interests me a lot. I think you didn't cover all of the benchmark available at this moment. I think if you look at the special issue on M4 competition, there is a paper specifically on combining prediction intervals. And there are quite a few benchmarks there. And if I remember the message correctly, the average actually didn't do that well. So some other forms of aggregation of confidence intervals did a little bit better than the average. So I think you need to include more benchmarks into your analysis. But other than this, thank you very much for an interesting presentation.
Very nice suggestions. And actually, we select 8 simple individual methods in our framework to conduct the forecast combination. And in the published paper, actually, we have compared our results with some other benchmark models in the M4 computation data. It's the best ranked methods results. So actually, our method may rank the second place. So thank you.
Okay, good. Yeah. Thank you.
Thank you.
Yeah, we could have one more question. And Xiaoqian, one more question I could ask. So do you think your work can be extended to other types of time series, for example, hierarchical time series data?
The structure of hierarchical time series data. You mean we determine the weights according this method for
I mean, in general, you put that into a hierarchical framework to make the forecasting interval over all hierarchies. Is that possible?
Actually, I have seen some papers on this, on your idea. They actually do this work.
Okay, thank you, Xiaoqian. Xiaoqian also is also our PhD student. So if you like her talk, please vote over Hoover. Thank you.
Thank you.
And I'm the last speaker. So I will share my screen. Yeah, can you check if screen is properly showed on? Okay, and thank you for attending this session. My name is Feng Li from Central University of Finance Economics. Currently, we work with EMF and our students, and we work on time series forecasting. Today, I'm going to present a particular topic on forecasting with distributed systems. I have revised the title a little bit to include some of our related recent work to make it much make people easier to follow. So we're going to talk about distributed forecasting with ultra long time series. Then we will introduce theoretical work. We worked based on least square approximation. Then we introduce a particular application for Bayesian VARs and with application to electricity demand data. So the ultra long time series are increasingly accumulated in many cases because nowadays we have new ways of collecting time series with apps, with the sensors. So we have much longer time series, and our time series are much higher frequency. For example, you could look at the electricity demand data, and you can also look at the temperature data from satellites. And another big portion of the time series data is the streaming data for internet companies. So they collect every minute or every second, personal behaviors over time. And it's not unrealistic to say that in future, all data in time series. And just if we need to, or if we wish to, or we have the ability to put the time dependency into our consideration. But forecasting ultra long time series is very challenging because we have to consider two factors. The first one is that in modern data science ecosystem, data are distributed stored in distributed file system. It's not like data stored in a single machine. It is distributed with many machines. But conventional time series models, we usually need to require time dependence. You really couldn't model the data independently. In that sense, then you will lose this time dependent characteristics. And from decision science perspective, we usually want to do a Bayesian model because Bayesian model is fully probabilistic, but training a Bayesian model is really time consuming, and model updating is difficult because sometimes the data comes really fast and you really need to make quick decision on run quick model that you have to include all historical data that is really demanding for machines. And the ultra long time series also requires ultra long forecast because you're not supposed to forecast the next second or next 2 seconds. You're supposed to forecast like next season or next year. So you have really long forecasting horizon. A particular example is the electricity demand data. At the household, you have this small sensor to collect the hourly or daily or even like minutes levels electricity consumption. And you at state level, you need to plan next season's electricity demand to balance its input and output. So that's really important for the from government point of view and to plan the future. And traditional time series model, we usually have assumption that is really strict. For example, we have a stationary assumption. Assume that time series mean and variance invariant over a long time. That is not realistic because you really couldn't think that in future nothing is the mean and variance doesn't change. And we don't see many Bayesian models in the applied industry. We visit some companies like our Chinese companies, Jingdong and Alibaba. They have heuristic models, but not Bayesian. So it's difficult for them to directly apply this long time series into probabilistic forecasting. And it's also making them very difficult to make inventory planning in business. So that's the purpose of why do we need to have this distributed forecasting for ultra long time series. Here we will see typical time series. It's not ultra long, it's pretty long. and it consists of 124,000 observations. When you observe scatter plot over time, you don't see any particular feature inside it. It's very difficult. And we need to forecast really long, like a quarter of the historical data. And for this type of series, it was popular in financial data, but now it's more and more popular in daily other industry. We'll spend a minute to briefly describe about distributed system framework for those people who don't know much about distributed system. On distributed system, there is a file system. It's like our Windows file system, but it's distributed with many, many computers. Each computer node consists of some hard disk, and each hard disk consists of a few blocks of time series. So if you have a million length of a million time series, that's like first 1,000 could be in the first machine, and the second 1,000 would be second machine, and so on and so forth. So you partition the whole data into small blocks. The modern distributed modeling scheme uses MapReduce scheme that first you have to make the model based on the first small chunk of the data, and the second and third, and those you can make it independently. In the end, you collect statistics, and you use a reducer, a particular program, to join those statistics, make a final model. The final model, then you can make each step forecast. That is a framework. We have to make a forecast model that works well with this MapReduce framework, so that is adaptable to industry. And we will introduce a framework that we have developed recently. It's called least square approximation. Assume that we have a loss function. We write it L, and we think if the loss function is twice differentiable. So, but this assumption can be relaxed in the future. If you write the loss function into the individual base, so loss function can be written in terms of a lot of individual observations, and we assume there exists a global optimizer aptitude that can find the optimal value so that the loss function get a minimum. If loss function is a negative likelihood, then this is the average of the negative likelihood. So it is interesting that we can decompose this loss function into a quadratic form by using Taylor expansion, so that loss function can be rewritten into this form, so that looks like quadratic, that is only connected to second order derivative and with constant. By optimizing this loss function, now is equivalent of having a solution for this quadratic form. And we notice that for this quadratic form, we can have an analytical solution for that. If we write this loss function for k different partitions, then that global loss function can be written into k sub-loss functions. And this work was based on our previous work published in JCJS. And we find some very nice properties that by doing this decomposition, our estimator is consistent with a global model. In terms of time series forecasting, having an estimator that is consistent with global model is not our ultra target. We want to say, can we do something similar or do something smarter so that we can take into consideration of the over long time period, and our stationary assumption can be relaxed. And this is exactly what we have done. Let's consider a var model that is a general var model. So you have a response variable with some lagged variables and some explanatory variable. In the end, you can write that into regression term. For this particular model, we are interested in two parameters, that is coefficients gamma and variance covariance matrix. We do this in a Bayesian framework that we can set up prior on two unknown parameters. We make it simple to make a uniform prior for gamma and psi, and that is Jeffreys prior. Based on that prior, it is very interesting. We can derive the conditional posterior from our interest of coefficients. And if you have the posterior, that's easy to get expectation and variance covariance matrix. That is all we need. This means that for a really long chunk of time, we could simply partition the data into small chunks. For each chunk, we can model a VAR model. For that VAR model, you can assume that locally there is a stationary assumption, but globally, you don't have to assume that for the over a very long time period that the time series is stationary. The non-stationary phenomenon can present gradually. By using our DLSA approach, we managed to have this posterior with ensembled by our previous parameters. If the posterior expectation and posterior variance is given, that is the finding. So we also extended to another scenario that assuming you build up a big model based on a huge historical data. Now it comes to a new day, and the new day you get some new data. You don't want to rerun the model for all historical data plus your new coming days data. So we apply the Bayesian scheme that yesterday's posterior, that is today's prior. So we summarize the posterior for historical data and put that as a prior for the newly incoming data, so that the posterior is always being updated. And in theory, you can guarantee that by doing this type of posterior prior updating, that is equivalent to have a super big machine for running a super model with the full data set. So with our approach, if we have some, let's make some notation. If the V-tilde inverse, that is presentation of the individual sigma inverse for individual machines position matrix, and also V1 tilde, that the initial one, and sigma tilde for the initial chunk of the data. When it comes to a new chunk of data, the new model's statistic can be updated based on the historical data and with the new data's position matrix. That is a very interesting finding. And this finding is also applied to other parameters like theta, and the theta is also updated based on the V you have and the previous V and the previous position matrix. By doing so, we can constantly update expected value for theta and the V. And this updating doesn't take much time. It's just a very simple matrix, and this matrix is not huge. This allows us to have real-time time series updating that you don't really need to run historical data, but also taking into the consideration of all historical data. In the industry, people, to achieve this model updating scheme, what do? They use a really short time period, and every time to run a model based on that small time window. There is a problem for that approach. You always forget history. If you forget history, and then when there was a phenomenon, when there is a situation happened in the long history, you forget it. And that particular situation may affect, for example, next year's or next 2 years forecast. You forget it, and that will not be considered. By doing our approach, you consider the historical data, and that historical data, the information also contributed to the current approach. There is one particular improvement that we can move some weight. So alpha is a weight based for different chunks of data. We can make the alpha to be stronger for the recent data and weaker to the very old data. So in that sense, you can have certain types of updating that you are more dependent to the most recent data and less dependent to historical data, but we still take historical information as a consideration as a prior. So we do application to what we said for the electricity data that the explanatory variables are explained here. For this time series, if we want to forecast the horizon that's pretty long, so we zoom in a little bit, you will notice that for every particular hour, you will see strong patterns. We've noticed that by doing distributed forecasting, we will save a lot of time. When you use ARIMA model, if you have a few P and Qs, you say for a traditional time, you have 4 minutes, and use our method, you have 1 minute. That doesn't save much time. But when you consider, when you have really long history memory, you need to include more legs. Using a ARIMA model, you have much longer time, and you our distributed system that is only like 1% of the overall time. This means for inventory planning and for industry, it really saves the computational cost. You can only use 1% of computational power to achieve a same forecasting accuracy, and we eventually see it can improve the forecasting accuracy. Here you will see forecast with ARIMA models that the green ones is that you make a global model forecast of the future because that is stationary. So you we forecast future that is like rectangle. But when you use our distributed scheme, you see there is a decreasing trend, and that is properly learned by the previous time period. That is very important for our finding. And we apply this to our electricity data. We forecast with different horizons, and when we use different loss functions and different metrics, MSE, MACE, and LPS, that is particularly used in Bayesian scheme called log predictive score. And we've noticed that for distributed system, there is optimal numbers of partitions that if you partition the data into optimal size, you can always achieve a much better forecasting accuracy. And this forecasting accuracy depends on the number of partitions and also depends on how long you would like to forecast. And discussions. In this paper, in this talk, we show that distributed forecast not only speed up computation, but also improve forecasting accuracy. And Xiaoqian's previous paper evident this. And there was a thing that distributed system like Apache Spark as a de facto standard in the data science, we have to make our forecasting model to be runnable and on this particular platform. And very unfortunately, we didn't see so many statisticians or forecasters are proficient with this system. And the scalable Bayesian forecasting models really empowers business planning. If you are interested in see our pure theoretical works, you can check our papers, for example, DLSA, that is for the distributed squares available on GCGS. We had a particular application to quantiles regression that is that appeared in GBES, and currently the DVAR model will be soon on arXiv, and the ARIMA model was already on arXiv. You could also try our software implemented with Apache Spark with this particular link, and feedbacks are welcome. Thank you. Welcome to check our lab, and welcome to visit us in person after the pandemic. Thank you. Any questions?
Hi, Feng.
Yes.
I've just got well, sort of one comment and one question, I guess. So the first thing is, this reminds me a lot of composite likelihood. So I just wonder
yes.
whether there's any connections there. And building on that a little bit, it feels like the model you're looking at, it's a VAR model, I'm assuming with Gaussian errors. So conjugacy
yes.
of the posterior seems to be important here. Do you have any ideas about how you can do this for non-conjugate posteriors?
Yeah, for this, as you mentioned for the first part, composite likelihood, it's not exactly same. And by doing this approach, it's much simpler and much straightforward. We don't have to go into that likelihood part. And by doing so, we can also do this lasso and variable selection and distributedly. That is the advantage of our approach and the one thing. And it's easy to make this to follow scenario from by moving code to date this philosophy. The second part, what you mentioned that is about, sorry, I forgot the question.
Conjugacy.
Conjugacy, yes. The conjugacy that is not required because we need to have, you could have the non-conjugate approach because the DLSA approach doesn't require really have that. Only if you can have a posterior summary. That means you have posterior expectation and posterior variance. That doesn't really require conjugacy. You can use conjugacy to get directly analytical form. If you don't have conjugacy, you can do sampling and you do the posterior summary for posterior mean and variance. That's my quick reply. Yes, does that answer your question?
It does, yeah, thank you.
Yeah, thank you, yeah. So you want to terminate this session so we can go to next session?
If I'm not mistaken, there's a break now, but we do have breaks in this program, a few of them. So I think there's a break now, but yeah, so there's no rush to terminate the session.
Can I ask a question?
Oh yeah, sure. Sorry, I didn't say it, sorry. Oh, Andrew,
okay.
Yes.
Thank you very much for an interesting presentation. It's a bit out of my comfort area, so my question might be silly, but when I was looking at the results in the visual form that you showed, where you were forecasting a stable period, and you're doing much better than original ARIMA, but you're kind of focusing on a very specific part of the data. With your algorithm, you can try forecasting different periods as well. So when you have spike, when you don't have spike, when you're just coming out of the spike, we're getting into spike. So I think it would be interesting to see how your method performs on other portions of the data, not on kind of relatively that looks like a little bit like stationary period.
Exactly. That's a very nice comment, and we haven't covered that part. And we may need to consider some Markov switching models or regime switching thing to handle that. And definitely, we're going to have a try. Thank you.
Okay. Thank you.
Yeah.
Can I ask you a question?
Yeah, sure.
How is the optimal partition number of partition determined? You said that if you choose the optimal numbers of partition, then you have increased performance. And how is that determined?
Yeah, currently we do like cross-validation thing. Say grid search, send it 1, 2, 3, 4, 5, and from Xiaoqian's paper, we noticed that there is, for example, you partition like 100 or 1,000. That's usually sufficient. We have a minimal requirement. Say, okay, you have to have each chunk of data to be sufficiently large to capture local features. That is minimal.
Can they overlap?
We try to avoid overlap, but doesn't significantly improve the accuracy. But that also affects the computational cost, because for distributed system, making the time series data overlapping is not properly designed in the hardware architecture.
Sure.
Yeah, so overlapping is very difficult, and also that requires heavy communication cost. So we didn't try that. We tried that, but it didn't work well.
Okay, thank you.
Yeah.
Thank you.
Yeah, thank you. Any more questions? Tas, are you raising your hands? No.
No, I raised my hand the first time, but then I just jumped in. So.
Okay, yeah, okay. Anyway, thank you for attending this session, and you're welcome to talk. We can talk over Whova, or we can talk over Twitter or whatever. And thank you. Let's go have a break.